Google recently released a white paper about a new coding agent that was able to improve on existing problems, long-standing problems of math and computer science that people have been working on, like partly for 59 years was the longest problem. And this coding agent was able to solve those problems. This coding agent was able to increase the efficiency of task scheduling in Google's data centers by 0.7%, which might not sound like a lot, but if you think about it, over the whole scale, all the data centers that Google has, they are now 0.7% more efficient. That means it's like they bought a million new computers, but without actually having to buy them, because just this algorithm found this new heuristic that made their scheduling way more efficient, way more, 0.7% more. Also, it increased the training efficiency of Gemini by 1%. And the fascinating thing about that is that Gemini is actually the underlying model that is powering this AlphaEvolve. So it kind of made itself more efficient, the training of itself. Also, it improved on 14 different matrix multiplication algorithms to bring them to better than state of the art. On many, it rediscovered the state of the art but couldn't improve it. But on those, actually, it managed to improve them. Most notably, the 4x4 matrix multiplication, which had like the current best. It sounds fancy. It's like current best was 49 operations, and now it can do in 48. Which is a big, huge improvement. And this problem was standing since, or like people were trying to prove this since 56 years. And this coding agent now found a better solution. Also, it was able to improve TPU design. TPU is like the chips that Google uses. It's a bit like a GPU, but special made by Google for like tensor processing unit. What they also run their AI on a bunch of their stuff on. And it was able to find some bits that are unnecessary that can be like left away for the next release, and therefore, just more efficient computation again. It also was able to improve about a bunch of math problems, and but I didn't list all of them here because I think in total they tried it on 50 different problems, and it improved 20% of them. And this is just the most noteworthy things that I listed here. But now, how does this thing work? I will first walk through how it works, and then short words on what are the implications for longevity. The goal of AlphaEvolve, what they give it is, it's something called program synthesis. So it creates a new program for a problem. And they do it in two different ways, depending on the problem. The first way is that they make it create a new, a better algorithm. So it's like directly, okay, we have this problem of matrix multiplication, and we want to find an algorithm that can do it in less steps than the current best algorithm. That is the first approach. The second approach, which I find completely fascinating, is that they evolve, they use this thing not to evolve the solution to the problem directly, but they use it to evolve a search algorithm that improves the solution, and thereby they find the best possible solution. So essentially, AlphaEvolve creates a search algorithm, and each time this, after it's evolved, they run the search algorithm for a certain amount of time. So let's say for I think 1,000 seconds. I think 1,000 was in the paper. So they run it for this fixed amount of time, and then they score if in that time it was able to improve the current best solution. So they give this algorithm the current best solution, the search algorithm and the current best solution. And if the search algorithm was able to improve, that's kind of their scoring. And then AlphaEvolve doesn't evolve the solution, but it evolves the search algorithm, which is applied again and again and again. And each time a new version of the search algorithms deployed on the problem, and thereby the search algorithm gets better and better, or especially it gets kind of more fine-grained, because in the beginning you can make a lot of progress quite easily or quite fast by a simple search algorithm, but over time this search algorithm has to become like really fine-tuned for like squeezing the last percentage out of the problem, and that is what they're doing with this second strategy, which I find absolutely fascinating and yeah, super cool. How does it work? Essentially, AlphaEvolve consists out of four parts. So you have a library of prompts, or like a prompt template. You have an ensemble of LLMs, so just simple Gemini models. They use two different, like Gemini Flash and I think Gemini Pro, so bigger and smaller ones. Then you have a function that evaluates what the AlphaEvolve builds, and you have a program database. I will go through all of the components now. So essentially, you start out by a human creating an initial program. You have an initial program that you give to AlphaEvolve, where you have some notations of points that you want to evolve. So you say, okay, I want to create this specific thing, and this is kind of my, either you just give like a skeleton of a program with empty functions, or you can already embed some of your knowledge. They tried different things, and they figured out that if you sometimes embed a bit of your knowledge and vary that around a bit, you have better performance than if you only give the raw empty program every time. But empty program also actually works. So with domain knowledge, you can give this first initial program, and this is then, I think it's also scored on the evaluation function, which you have to define before. The important thing is this evaluation function has to work quick on a computer, like relatively quick. It is okay if it takes a while, but it has to run automatically, because if you have to do like a month experiment to test whether one idea of AlphaEvolve works, then this would not be practical. And then this program is given to the LLM, and there is a prompt template where it's put in and it says like, okay, this is our current best program, please improve that. So it writes a new version of this program, an improved version with the goal in mind that is in the prompt, and then this is evaluated and it is scored. So you have multiple scores. What they say is important to use multiple scoring metrics, so they don't only use on the exact performance on the problem. Like, let's say we want to improve matrix multiplication. You could say, okay, my only thing that I care about is the number of operations it takes. But what they figured out, it helps if you have multiple evaluation metrics, like for example, simplicity of a program, stuff like that. And they actually scored that with another LLM. So they have a large language model score, because simplicity of a program, you can't really score it by counting number of lines, because that could lead to super complicated lines or whatever. So using a large language model to score simplicity, and a bunch of other things. Then you have your programs, and you have the scores of the programs, and each time after one new program is evolved, this is added to the, if it passes the minimum requirements, it's added to the program database. And then in the next round, some programs of the are sampled from the database, and it gets essentially like a list of programs with like, okay, we have those ideas with those scores, and then it gets one specific one that it's said that it should evolve. So first a couple of examples from the database, and then one example from the database where it's like, okay, this one we want to evolve. And then it can kind of use ideas from the top ones or its own ideas that are in the model itself to create diffs. So like create some changes that it wants to make to this last program. And it suggests those changes. Those changes are applied, it's evaluated, and if it works, it's added to the database, and that again and again and again and again. And that's essentially how it works. So in the end, you have this loop in which it always gets programs that it previously created, and then it's told to improve those programs. It's essentially just like an evolutionary algorithm, just that the evolution here is not random. It's a large language model that is doing the evolution, and therefore it can ingest its domain knowledge, and it can. There's a way more efficient type of improvement of the program because they are using this large language model. And some interesting things that I found are that first, using different types of large language models is kind of optimal. So if you only use the small ones, the performance is a bit worse, but they still use small ones and big ones in concert, like sometimes this, because the small ones can run way faster. You don't need as much compute for them, but the big ones sometimes give better ideas. So if you kind of mix them up, then you have a high throughput of new ideas, but at the same time you also have like this occasional really good ideas that really or you have the chance for really good ideas that really push the problem forward. And another thing that I find fascinating is that for the prompting, like what I say, it helps to have random prompts that you kind of sample, or not random, but you have a library of prompts and you sample from them to have like more variance in the results. But what is fascinating is that they use something that they call meta prompting, which is that a separate large language model, which is working quite similar in a similar loop like AlphaEvolve, evolves refined versions of the prompt template while it is working. So it kind of iteratively improves the prompt template while getting feedback on the prompts, and therefore the prompt is getting better while AlphaEvolve is evolving the new program, and incredibly fascinating for me. Next slide. What are the implications for longevity on that one? There is a bit of a problem. It sounds amazing. It sounds like, wow, most of our problems are solved. We can just put them in there and it will iteratively figure out the solution. But the problem is that AlphaEvolve doesn't. It requires that the problem that it's trying to solve is easily verifiable. Like a solution is easily verifiable. Like the quality of the solution is easily verifiable with a computer. And the problem for longevity and biology is that most solutions are not easily verifiable in a computer. Most solutions are cost millions to verify in clinical trials. So if we, the question how can we use this for longevity is we have to find either sub-problems of longevity where we can actually validate with a computer. There's also the idea of using large language model feedback. So as I said, like simplicity of a program was scored by another large language model. So if you have something where a good solution is easily to recognize by a large language model, you could also use this as a feedback, but it's quite hard because this is not a hard number. This is it might just evolve the most convincing sounding solution, which in the end is not based in reality because it's an LLM creating stuff that is validated by another LLM without any grounding in reality. So we need this grounding in reality that can be checked by a computer. Like maybe there's some way to mix this with ideas like AlphaFold for protein folding, like use that as a measure for reality and combine it in that way. But in a sense, it's going to be hard to use that. But I'm completely fascinated, and I definitely want to look into the opportunities that we have to use this because, I remember all my discussions with friends. Large language model can never make scientific discoveries, and now they figure out a way how they can use it and how they can actually use maybe even hallucinations if you properly score them through this evolutionary approach to get better and better and better solutions to problems. For people not listening to this as a podcast but watching it, there's here the sources I have. It's one, the white paper, and just on their website. That was it. See you in the next one.